Hello, everybody. Mr. Huntley here, trying something new. We're trying to do this screencasting with Zoom to see if it works any better. We'll be able to embed the links so we can watch the videos together, which might make it easier, but we'll have to wait and find out. So please let me know via email or in the in-class chat if you like this better or worse. I'm just trying to make it as usable and as easy for you guys as possible. All right, so we're going to start out with part 2 of our Big Bang slides. And basically, we had this idea that the Big Bang happened, but how do we as scientists back it up, right? Because in science, we can't just say, oh, great, yeah, let's say this happened. Sure, let's go with that. We can't do that because we have to back up everything we say with evidence. And it's important that we have this evidence. So today we're going to talk about the evidence of the Big Bang, how and why we think it happened the way that it happened. In science, we can't prove anything, right? So there are people out there that will say the Big Bang didn't happen, but it's strongly believed that in the scientific community that the Big Bang did happen because of these forms of evidence. Let me see if I can advance a slide. All right, so evidence one we're going to talk about is redshift. And in 1929, I was practicing this, so let's see if I can get it right. Georges Lemaitre, it's French, I had to practice. Georges Lemaitre had thought, seeing a red hue around some distant stars, that there was a red shift that was happening. And thus, this was sort of the first thing that was said, hey, if there's red shift, that means things are moving. And if things are moving, that means things could have had moving the whole time. And if we did more on the end of it later, but right now, he was the first person to figure out redshift. 1929, so not that long ago, not even 100 years ago, was the idea of this redshift. And we'll talk more about redshift here. When things are moving away from us, we will say that I have a redshift, and things are moving towards us, they'll have a blue shift. And I know that's kind of confusing. And in fact, I know it's probably really confusing, but we will get there. But what I need you to know for this slide, at least, the Georges Lemaitre was the first to identify red shift. He was the first guy to come up with it. Okay, and again, on my slides, if it's in a colored font, that's the important stuff. If it's in a gray or white font, we don't really need to worry about it so much. Okay, so redshift. Strap in. This is not the easiest concept. First, light and sound waves travel in waves. So when you see a light, it is a light wave. Your eye perceives it as a wave, and your eye adjusts for it and figures it out and processes it and puts it in your brain. And then you see red, or you see blue, or you see green, whatever. We're not going to really talk about waves so much in here. There's a lot of things you can know about waves, but we won't go into it because, one, we don't have enough time, and two, we're just not going to go there. It's not part of our job. But if you do take physics from me or Mr. Sullivan, we will go into waves and do a whole unit on waves because they are very interesting. And like I said, light and sound both travel in waves. So the words that you're hearing, well, you're not actually hearing my words because you're not sitting with me, but your speaker is putting out sound waves to you, and the way it beats and pushes the air around makes you hear my voice. And that's sort of how sound waves work. Sound waves and light waves are different. One's a transverse wave, one's a longitudinal wave. You don't need to know those words, but they are different. But they follow the same general rules. They oscillate, they make a repeatable pattern. They repeat motions. Some things oscillate faster, some things oscillate slower. The quicker oscillating waves are high-pitched. So if someone has a really high voice, they're going with a higher oscillating frequency. And if something has a low voice, that would be a slower oscillating wave. Or in the color world, right? I think it's easy to look at high and low pitched when you think about sound waves. But in the color world, if something is high pitched, it's more blue. And if something is longer pitched, it's red. And the way I try to remember this is, if you look at a rainbow, I think we've all seen rainbows in our life. The wave on the outside of the rainbow is red because it's longer. It travels a farther distance because it's on the outside of the circle, versus the blue wave, which is on the inside of the circle, travels shorter distances. So the shorter waves are blue, the longer waves are red. And actually, that's why a rainbow looks the way it does. But you didn't know you get a rainbow lesson today. So how does this help us? So this is where we get the whole idea of Doppler effect. that you should write down. Doppler effect. It's right there as I'm pointing on my screen. Doppler effect, EFFECT. So when things are moving away or towards you, the Doppler effect says they're going to change the frequency, either red or blue or high pitched or low pitched. And we have a couple videos here, which I assume play for you. We're going to give that a shot. Doppler effect.
Doppler effect in light waves. In our earlier session, we have learned about Doppler effect in sound. Now, let us learn about Doppler effect in light. The physicist had first found Doppler effect in sound waves. Later, he applied same to light waves. In case of light, due to Doppler effect, when the source of light is moving to...
So, go away. So what I want you to look at in this video, I know this stuff is a little bit advanced and some of you guys are probably like, what the hell is going on? Just bear with me, okay? What I really want you to look at, what I want you to understand is when this white ball of light is moving from the guy on the left to the girl on the right, as it's moving, it's squishing up these waves in the front of it and it's stretching out the waves in the back of it. And that's really the idea of the Doppler effect, right? When these waves get squished together, it increases the frequency. You're getting the waves quicker, right? They're as if these waves were to go out and to hit that girl's ears or that girl's eyes, the waves would seem closer together because the source is moving towards her. Because of that, it's going to have a more bluish tendency or a higher pitch tendency. And the same thing is for this guy in the backside. As these waves come spread out farther and farther, they're going to seem slower and slower because the source is going farther away. And we'll talk more about this. I got a couple videos, I got a couple slides. So if you don't understand on the first video, don't freak out. We'll get there.
Towards the observer, the frequency of emitted light changes. When the frequency of the sound wave changes, the intensity of the sound also changes. When the frequency of light wave changes, the color of light also changes. If we see at visible spectrum, we will find that red light has longer wavelength and blue light has shorter wavelength. So, if any shift towards longer wavelength, it is said to be as red shift, and any shift towards shorter wavelength is said to be as blue shift. The change in frequency is same as change in wavelength. Longer wavelength has lower frequency and shorter wavelength has higher frequency. As per Doppler effect, when source moves towards us, it has high frequency with lower wavelength, and then the shift is blue shift. When source is away from us, it has lower frequency with higher wavelength, and then the shift is red shift. The Doppler effect in light can be seen with the help of device called as spectroscope.
All right, so that was one video. Here's a couple more. You can see down here, we're still talking about the Doppler effect. I'm just trying to give you guys a couple different outlooks so that you guys can hopefully grab onto something here. This one I think is a little bit more, possibly more appropriate for you guys, just because I think it's a little younger and maybe a little bit more your speed.
Science, fun science, fun science, it's a science of fun, yeah. Today I'd like to tell you some cool things about light. Now, as I'm sure you're aware, the speed of light is 299,792,458 meters per second, which is pretty bloomin' fast. To give you an idea as to how fast that actually is, it would take a beam of light 1.255 seconds to travel from the Earth to the moon. The speed of sound is only 340 meters per second, which is still pretty fast, even though, thanks to science, humans have managed to go faster than that. But if you want to go faster than light, then sorry, you can't. It's not possible. It's theoretically possible that we could one day travel very, very nearly almost as fast as light, but to go faster than that, no, sorry. Now, before I can tell you about all of the really cool stuff that comes with light and the speed of light, I have to tell you about this other thing called the Doppler effect, which is still really interesting, so, don't leave just yet. The Doppler effect is the change that you notice in the frequency of a wave when the source of that wave is moving relative to you. For example, imagine that you're sitting by a canal enjoying the lovely British weather when suddenly I appear next to you screaming like a lunatic. From your perspective, it's just really, really weird. However, if theoretically I wasn't standing next to you but was running past you at 80 miles an hour, still screaming just as I was before, as I approach you, the pitch of my scream would be higher. And then as I pass and run away from you, the pitch of my scream would drop, even though from my perspective, I'm screaming at exactly the same pitch as I was when I was standing still. The reason this shift in pitch happens is because when I'm sitting still and screaming, the sound waves are emitting from my mouth uniformly. But when I start moving, the sound waves in front of me get squished up and the sound waves behind me get stretched out. And it's this change in the frequency that causes the change in pitch as I pass, and that is what the Doppler effect is. The reason the Doppler effect is important is because it doesn't just apply to sound, but it also applies to light. Bet you didn't see that one coming, because it's not a video about light or anything like that, is it? So just as when something is moving and emitting sound, you can hear a difference in the pitch of that sound, when something is moving and emitting or reflecting light, you can see a difference in the colour of that light. For example, imagine that we're in exactly the same running canal situation as before, except this time I'm not screaming like a lunatic, and instead of running at 80 miles an hour, I'm running at very, very nearly almost the speed of light. What would you see? Well, you probably wouldn't see anything at all, because as you'll remember, the speed of light is very, very, very fast, and I'd be gone before you even knew I was there. But let's pretend that you had a magic iPhone app that would let you take pictures of me traveling very nearly at the speed of light. What would you see? Well, when I'm running towards you, the light in front of me gets squished, and the frequency of that light gets shifted to the blue end of the visible light spectrum, and so I appear blue. And then as you see me running away from you, the same thing happens in reverse. The light behind me gets stretched out, shifts to the red end of the spectrum, and then I appear to be slightly red. Now, this change in the frequency of light is something that happens all the time. In fact, it's happening right now as I move forwards and backwards from you, but the change is so negligible that you can't notice it unless something is traveling at very, very nearly the speed of light. But easily the coolest thing that happens when you travel at very, very nearly almost the speed of light is that when you do, time slows down. All clocks, whether man-made or biological, like me, ticks.
The rest of this video is highly unneeded, but we can watch it anyways because there's only half a minute left.
Slower when you're traveling that fast. So back to our thought experiment where I have the ability to run very nearly at the speed of light. Imagine that I decided to take a couple of minute tour around London traveling that fast. Well, it might have only seemed like a couple of minutes to me, but to you, traveling at normal human speed, it would have been many, many years. And so by the time I returned from my very short run, you would have died of old age. And that, ladies and gentlemen, is light. This is the end. Bye.
You've just had the almost
Okay, so again, another example of what redshift and blue shift does when things are moving towards and away from you, okay? The time dilation bit at the end, again, if you want to learn about time dilation and you're that kind of person, go ahead and learn about it. It's really fascinating stuff, but I'm not going to require it in this class because you guys are freshmen and this is Science 9, so we don't get there. But yeah, so when things are moving away, key takeaways, when things are moving away, they're going to appear reddish, the wavelengths are going to stretch out, the frequency is going to drop, and when things are coming towards you, the frequency is going to go up, the wavelength is going to go down, and they're going to appear blue, okay? So like, that's the takeaway from the Doppler effect. All right, so trying to give you guys a way to think about this in a way that isn't a video and trying to think about this in a way that isn't in some weird accent, which is, I don't know, today's episode of Science 9B is brought to you by people with accents. So let's say that Frankie Fastball can throw a baseball at 75 miles per hour and he can throw 5 baseballs in 5 seconds. Okay, that seems doable, right? So if you're someone's throwing boom, 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 and you would catch the ball and it would be boom, 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 right? That seems like that makes some sense. Okay, so now the number of times you catch the ball is called the frequency, right? So every time you catch it, that's a beat, a beat, a beat, a beat. Now, if Frankie was on a conveyor belt and moving away from you as he threw his baseballs, the distance between you and Frankie would be increasing. Therefore, it would take longer for that baseball to get to you than original, because instead of being like 50 feet away, he'd be 75 feet away and 100 feet away and 125 feet away. And so the idea that you would catch one ball and then it would take longer to catch the second ball because it was traveling a longer distance, and then you'd catch a third ball, it would take longer yet. So like the idea of that frequency getting stretched out as he was moving away from you makes some sense, right? And the opposite can be said if he was on a conveyor belt and he was moving towards you at a high rate of speed, the balls would get to you faster as he got closer. And if he was actually on a conveyor belt moving 74 miles an hour, he would throw one ball and he would keep up with it. As he threw the second ball, it would be almost right next to the first ball, right? And then this third ball, fourth ball. So you would catch all 5 balls, boom, 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 right? So that is sort of a real world, as much as I can break it down, idea of this idea of redshift. So I want you to understand the redshift. As things are moving towards you, they're blue, the frequency goes up, and if they're moving away from you, the frequency goes down and they're red. All right, so now back to the main trade. So we've gone through all this redshift. So congratulations, you are now all redshift experts. And he had this great idea. And he said, I think that things are moving away from us because everything has this idea of redshift, right? And so if something is red, it's moving away from us. So he's now using the idea of redshift and saying, if it is red, it must be moving away from us. Otherwise, it wouldn't be. But he couldn't really prove it. And he had some strong people that opposed him, strong scientific community people like Albert Einstein, who he's kind of famous, didn't really like the idea. And like most scientific things, people don't like them right away until we can back them up more and more. So he didn't really have proof until a guy named Edwin Hubble gave evidence to Lemaitre's ideas. And he found that all galaxies were redshifted, all of them. So everything was moving away from Earth. And the things that were farther away from Earth were actually more redshifted and therefore moving faster, because the faster you go, the more the redshifting happens, right? If you were on the conveyor belt moving away from me at a super fast rate of speed, like the balls wouldn't, not exactly a great analogy this way, but like the balls would take longer and longer and they'd be more shifted out and things like that. So there he is. This is Edwin Hubble. This is his fancy telescope, which is called the Hubble telescope. It's in space currently, and it does a great job looking at things. They wanted a telescope out in space because the Earth's atmosphere actually blocks a lot of what we can see. Yeah, all those air particles in the way, actually, as we don't think about it. But if you think about it, you can, on a cloudy day or a place that has smog or something like that, like it does affect your visibility. So if you go outside the atmosphere, you can actually see a lot better. So that's why they put a satellite in space, and it's actually named after Edwin Hubble. He found that they were moving away. And actually, if you look, if I can get that stupid thing off the screen, you look and you can see that as the distance increases, the speed and the velocity of the stars actually goes up, and it's actually a super linear line, which is important. This Hubble's law idea is important. So things that are farther away from us are moving faster than things that are close to us. And so, yet everything is moving away from us. So does that mean we're the center of the universe? Well, you would think so, but not quite. And you'll see why here in a slide or two. So redshift is happening. And then, oh my gosh, not only is redshift happening, but it's happening like in a definite pattern, right? It's not just happenstance. There's not like this one's moving red, this one's moving blue, this one's moving super red, this one's moving kind of blue, and this one's not moving at all. They're all red, 1. And 2, the farther away ones are moving faster than the closer ones. So if you might need to pause this to write all this down, it's a pretty big, I just set it up, so I'm not going to take too much longer, but there's a definite linear relationship. to how quickly they're spreading away from us and how far away they are. And then finally, I think this one, this, are we the center of the universe? Gosh, it would be awesome if we were, but sorry. Oh, guess what? It's gonna be a good video. You can just tell by the intro. Look at this.
This may seem like a simple question. Since the universe is expanding, it would seem logical that it was expanding away from a particular point. But the universe doesn't actually work like that.
Water break.
The Big Bang, which started the expansion of the universe, isn't like a firecracker explosion where there's a boom and all the pieces go flying apart from a single point. The Big Bang was in fact the creation of matter and space, and it is this space that's expanding. Think of space as if it's a sidewalk with people standing on it. The expansion of the universe isn't the people walking away from each other, but it's more like the sidewalk is spreading and moving the people apart.
So just to take a second, why is this stupid thing happen every time? Just take a second. This is pretty heady stuff. Again, because we talked about the Big Bang yesterday was the creation of space. So things aren't like traveling through space. This is what he's trying to say. Things aren't really traveling through space like you and I travel through the world, right? Like if I drive to someone's house, I'm driving through Earth, right, to get there. His thought process here, and it's agreed upon, so it's not just him, but like it's the expansion of space itself, and we're kind of just like we're in this idea of space, and the space is expanding, and so we're all just expanding with it. That's the idea here. So these guys on the outside aren't exactly walking along the sidewalk to get farther away from the first guy. Look at these guys, social distancing. Who knew, right? But it's the sidewalk itself that's moving and spreading, and it's taking the people with them and spreading them out as well.
As a simpler example, let's take the surface of a balloon. We can draw galaxies on it, but notice that no galaxy is at the center of the surface. When we blow up the balloon, all the galaxies spread apart from each other. If you look at any single galaxy, all the other galaxies seem to be spreading away from it. Every galaxy sees itself as the center of the expansion, but since not every point can be the center, that really means there is no center. The more space there is between any two galaxies, the more the expansion will be pushing those galaxies apart. So the further away one galaxy is from another, the faster it will be expanding away from it. This discovery was made in 1929 by Edwin Hubble, who discovered that the further away a galaxy is, the faster it was receding from us.
Man, I wish I
That's
had a
now known
pipe.
as the Hubble law. The rate of expansion of the universe is now known as the Hubble constant. So even though it looks like we're at the center
It's an
of the
interesting
universe,
background he has
the universe
behind him.
doesn't actually have a center. For Ask an Astronomer, I'm Dr. Varujan Gorgian for NASA Spitzer Science Center.
All right, so there you go. Are we the center? No. And I think the interesting thing, no matter where we are, if we were to travel, if we had the ability to travel to a distant star like 84 light years away, whatever, and we set up a cool telescope there and we looked out, everything would be redshifted from there too, right? Because no matter where you are, everything is traveling away from you, because either if you're farther away, that means the things farther away from you are going faster, and if the things behind you are going slower, you're still spreading apart, right? Think of like a 100-meter race. If you had a really fast person, a kind of fast person, and then a slow person, the slow person sees the fast two people spreading apart from him. The fast person, if he looks behind, will be leaving the slower people behind. And the middle person, the fast person will be going faster ahead of him, and the slower person will be farther behind him. So no matter which person you look at, fast, medium, or slow, you're going to be spreading apart. Right? So that's the idea of this whole idea of moving everything. Everything is always redshifted. All right, and then evidence 3, and I told you to look at the background behind the guy, and it looks a lot like that. So even after this whole idea of redshift, even after this whole idea of everything's moving at a set speed, and you can figure how far away something is by how fast it's going, and you can figure how fast something is going by how far away it is, there were still people that were like, nah, that's crazy. You know, like that doesn't work. It doesn't work. It doesn't, because what if this, what if that, la, la. And then back in 1964, so again, not long ago at all. Now this is almost 50 years ago. Two guys, Arno Penzas, yep, I don't know how to say that, and Robert Wilson, I feel more confident with that one, found further background. So they were trying to do an experiment, and they kept getting this weird hum in the back of their experiment. And they did it, and then they went and they cleaned their instruments, thinking, okay, there must be something up there. They thought it was pigeons actually on their little satellite dish. They got the pigeons off. They did it again, same hum. They just kept getting the same hum, kept getting the same hum, and it was kind of uniform. No matter where they pointed, they would get this weird hum, and they couldn't figure out what it was until finally, and this is why you never throw away your data in science, they found that it was this cosmic background radiation. So we talked about the radiation era back in the Big Bang on day one, and everything was radiation. It was just heat and energy and blah. It was just crazy. And elements couldn't even form it because it was so hot, so nuts. But what these two found, actually, and won a Nobel Prize for, was that there's still cosmic radiation in space everywhere. Like it's not as hot as it used to be, right? It's not as much as it used to be, but there's still some everywhere, no matter where you look. So this is basically the idea that the solar system is still having repercussions from the Big Bang. Like it's still cooling down. It's still trying to get back down to normalcy. That's how hot and how intense that thing was, that 14 billion years later, it's still out there and it's still cooling down. So evidence 1, redshift. Evidence 2, the idea that galaxies there's a linear path, and so things moving faster are farther, things moving closer are not quite as redshifted. And this idea that this cosmic background radiation is still there is the 3 main pillars of evidence that the Big Bang happened. So it's not like we're just making it up. It's not like we're just hoping, but in fact, there is some credible evidence that we need to realize and we need to use to our advantage, okay? So that is all I have for today's lesson. I hope you enjoyed it. I hope it sounds good. Please let me know if it doesn't, and I can try to keep tinkering with this. As you notice, I am upstairs today, so it's very exciting. I have a tree. There it is. And a poster. And a light. And a hockey hat. Go Roseville. All right, hope you guys enjoyed it. I will talk to you soon. Bye.